Our universe is a place of wonder, filled with celestial objects of unimaginable size and power. From the swirling galaxies that span millions of light years to the twinkling stars that dot our night sky, the cosmos is a vast and awe-inspiring expanse. Amidst this vast cosmic dance, there exists a fundamental force that governs the interactions of everything from the smallest particles to the largest galaxies' gravity. This force is the silent architect of the universe, orchestrating the movements and interactions of celestial bodies on a grand scale. It is an invisible tether that binds the universe together, dictating the motion of planets, stars, and even light itself. Gravity's influence is so profound that it can bend the very fabric of space and time, creating phenomena such as black holes and gravitational lensing. Gravity keeps our feet firmly planted on Earth, preventing us from floating off into space. It is the force that gives us weight and allows us to walk, run, and jump. Without gravity, life as we know it would be impossible. It is the force responsible for the rhythmic ebb and flow of ocean tides, influenced by the gravitational pull of the moon and the sun. The tides are a constant reminder of the moon's presence and its gravitational influence on our planet. This invisible force is not confined to our planet alone. It extends its reach far beyond, holding our solar system together and shaping the grand structure of the cosmos. Gravity is the glue that binds galaxies, clusters, and superclusters, creating the intricate web of the universe. Despite its pervasive influence, gravity remains one of the most enigmatic forces in the universe. Scientists have long been fascinated by its mysteries, striving to understand how it works and why it exists in the form that it does. Scientists have dedicated centuries to unraveling its secrets, seeking to comprehend its true nature and its role in the evolution of the cosmos. From the early observations of Galileo and Newton to the groundbreaking theories of Einstein, the study of gravity has been a central pursuit in the field of physics. The quest to understand gravity has led to some of the most profound scientific discoveries in human history, forever changing our understanding of the universe we inhabit. Einstein's theory of general relativity revolutionized our perception of gravity, revealing it as a curvature of space-time caused by mass and energy. More recently, the detection of gravitational waves has opened a new window into the cosmos, allowing us to observe the universe in ways never before possible. As we continue to explore the depths of space and push the boundaries of our knowledge, gravity remains a key focus of scientific inquiry. Its mysteries continue to challenge and inspire us, driving us to seek a deeper understanding of the universe and our place within it. The unseen force that shapes our world is a testament to the beauty and complexity of the cosmos, reminding us of the endless wonders that await our discovery. The story of gravity is often told beginning with a falling apple. This simple yet profound moment is said to have sparked a revolutionary idea in the mind of one of history's greatest scientists. That brilliant mind belonged to none other than Isaac Newton, a man whose curiosity and intellect would change the course of science forever. While the tale of the apple may be apocryphal, it serves as a powerful metaphor for Newton's groundbreaking insight into the nature of this fundamental force. The falling apple symbolizes the moment of clarity that led Newton to formulate his theories on gravity. In the 17th century, Newton proposed that every object in the universe attracts every other object with a force that is proportional to their masses and inversely proportional to the square of the distance between them. This was a radical departure from the prevailing scientific thought of the time. This simple yet elegant law of universal gravitation revolutionized our understanding of the cosmos. It provided a mathematical framework that could predict the motion of planets, stars, and even galaxies. It explained why objects fall to the ground, a phenomenon that had puzzled humans for millennia. It also explained why the moon orbits the Earth, a celestial dance that had been observed since ancient times but never fully understood, and it clarified why planets revolve around the sun, supporting the heliocentric model proposed by Copernicus and further developed by Kepler. Newton's law of gravity provided a unified framework for understanding the motion of celestial objects, demystifying the heavens and laying the foundation for modern physics. His work bridged the gap between the terrestrial and the celestial, showing that the same laws applied to both. Newton's work was a triumph of human ingenuity, but it did not provide all the answers. His theories were groundbreaking, yet they left some questions unresolved. While his law accurately described the force of gravity, it did not explain how this force acted over vast distances of empty space. The concept of action at a distance was perplexing and would remain a topic of debate and investigation. The mechanism by which gravity exerted its influence remained a mystery, a puzzle that would captivate scientists for centuries to come. It wasn't until the 20th century, with the advent of Einstein's theory of general relativity, that a deeper understanding of gravity began to emerge. Einstein proposed that gravity is not a force transmitted through space, but rather a curvature of space-time itself. This revolutionary idea built upon Newton's work and provided a more comprehensive explanation of gravitational phenomena. Today, scientists continue to explore the mysteries of gravity, using advanced technology to study gravitational waves and the behavior of black holes. Newton's revolutionary idea, sparked by a falling fruit, set humanity on a path of discovery that continues to this day. Newton's law of gravitation, while revolutionary, left some questions unanswered. Sir Isaac Newton's groundbreaking work in the 17th century laid the foundation for classical mechanics and our understanding of gravity. His law of universal gravitation described how every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This was a monumental leap in science, yet it wasn't the complete picture. How could gravity act across the vast emptiness of space? This question puzzled scientists for centuries. The idea that two objects could exert a force on each other without any physical connection seemed almost magical. What was the medium through which this force was transmitted? Many scientists of Newton's time and later speculated about the existence of a mysterious substance called ether that filled space and carried gravitational forces. Scientists struggled with these questions, searching for a deeper understanding of gravity's enigmatic nature. The quest to understand gravity led to numerous experiments and theoretical developments over the centuries. The answer, it turned out, lay in a radical reimagining of the very fabric of the universe. This new perspective would not only address the shortcomings of Newton's theory, but also open up new realms of understanding in physics. In the early 20th century, Albert Einstein, a physicist of unparalleled genius, proposed his theory of general relativity, which would forever change our understanding of gravity. Einstein's insights were revolutionary, offering a new way to think about space, time, and gravity. Einstein's theory dispensed with the need for a mysterious force acting at a distance. Instead of relying on the concept of ether or an invisible force, he introduced a new framework. Instead, he proposed that gravity was not a force at all, but rather a manifestation of the curvature of space-time itself. This was a profound shift in thinking, suggesting that massive objects cause space-time to curve, and this curvature directs the motion of objects. Imagine a bowling ball placed on a stretched rubber sheet. This simple analogy helps to visualize Einstein's concept. The ball's mass causes the sheet to sag, creating a depression. This depression represents the curvature of space-time caused by a massive object. Now imagine rolling a marble across the sheet. As the marble moves, it follows the contours of the depression. The marble's path will curve as it approaches the bowling ball, drawn towards it by the depression in the sheet. This is analogous to how objects move in the curved space-time around a massive body. This, Einstein argued, is analogous to how gravity works. The curvature of space-time guides the motion of planets, stars, and even light. Massive objects like stars and planets warp the fabric of space-time, and other objects, including light, follow curved paths through this warped space-time. This elegant theory not only explained the motion of planets, but also predicted phenomena such as the bending of light around massive objects, which has been confirmed by numerous observations and experiments. Einstein's general relativity remains one of the cornerstones of modern physics, continuing to inspire and challenge our understanding of the universe. Section 4. Einstein's insight, reimagining gravity as the curvature of space and time. Einstein's theory of general relativity was a profound departure from the Newtonian view of gravity. It proposed that space and time were not absolute and unchanging, as Newton had believed, but were dynamic and interconnected, forming a four-dimensional fabric known as space-time. Massive objects, according to Einstein, warped this fabric, much like a bowling ball deforms a stretched rubber sheet. This warping of space-time is what we experience as gravity. Objects moving through space-time follow the curves created by massive objects, just as the marble rolling on the rubber sheet is drawn towards the bowling ball. The more massive the object, the greater the curvature it creates in space-time, and the stronger its gravitational pull. Einstein's theory made a number of startling predictions, many of which have been confirmed by subsequent observations. It predicted that light, which was thought to travel in straight lines, would be bent by the gravitational pull of massive objects. This prediction was famously confirmed during a solar eclipse in 1919, when astronomers observed the bending of starlight as it passed close to the Sun. Section 5. Gravity's impact, from tides to the structure of the cosmos. Gravity, despite its relative weakness compared to other fundamental forces, plays a pivotal role in shaping the universe at all scales. It is the force responsible for the formation of stars and planets, the intricate dance of galaxies, and the very structure of the cosmos. On Earth, we experience gravity's influence in countless ways. It keeps our feet firmly planted on the ground, governs the trajectory of projectiles, and dictates the flow of rivers. The rhythmic ebb and flow of ocean tides are a testament to the gravitational pull of the moon and the sun, a cosmic dance that has shaped our planet for billions of years. Beyond our planet, gravity's influence is no less profound. It holds our solar system together, keeping the planets in orbit around the sun. Gravity governs the motion of stars within galaxies, creating the swirling spiral arms and elliptical shapes we observe in the night sky. And on the largest scales, gravity is the architect of the universe's grand structure, drawing matter together to form vast clusters of galaxies.